I probably didn't see any of your.
Hey, what time are we on? We have 4 minutes. Technically 9.
We follow.
Sorry. There we go. Hey, how's it going? Pretty good. How about yourself?
Doesn't it, bro? Maybe, yeah, you've grown into irrelevance.
I still have my books on Discord. Like all
Wait, so how many people were there?
like
They don't recommend it.
what I did is I started building machine that just
Okay, okay.
I was yeah, like it was an one. I was when I go to play a game. Well, yes, you're making this.
I better see you there.
Yes.
It's not a hybrid section.
Can you talk about logistics? Yeah. Mention money from this last quarter.
All right, hello everyone. We'll start in a couple minutes. Usually we start at 6:05 just to give people time to come in. Classes, probably used to that kind of thing.
Okay, this is anything. I have to.
Yeah.
Can I ask you a question on GANs?
Sure.
Go for it. Okay, with the example, can you use some sort of OCR to verify the text is correct? If you want to generate a specific image?
Technically you can, right? I mean, depends on how well your text detection software is. And
If you use something like Tesseract, which is I think it's considered like the best open source library for OCR.
yeah, I mean, you can use that as like a detect to see how well your GAN's running and make an automated process for changing up the network, how it trains the GAN.
So yeah, would that be good for calculating loss?
Yes, yeah, that would be, but I mean, that's a specific example, like you said, about checking for text, right?
Yeah.
So I mean, if you want to do anything other than checking for text, you can use all sorts of different methods, which is why you have the concept of the discriminator. It's supposed to learn how to identify the end. Yeah, we'll get into all this stuff later.
Also, part of the issue with GANs is that they don't really understand the concept of functional text. Like you can generate stuff that looks like text, but you're not going to get something that makes a lot of sense. I don't know if there have been developments, but generally my understanding of GANs and a lot of diffusion models as well, which we'll get into in a couple of weeks. Text that ends up getting put out is either gibberish or just wrong. It looks like words, so the computer's like, all right, that's good, man.
It knows shapes and symbols, but it doesn't know.
Yeah.
Is that what NLP is for?
Yes, exactly. NLP is what connects and knows what different words relate to other words and how letters combine and stuff.
Yeah. Oversimplification, but
yeah, oh yes. Yeah,
it's huge. Don't worry about it. All this stuff we'll cover at some point, or who knows. It's the neat part about doing things in machine learning. It keeps getting better all the time, and there's so much we'll never run out of things to talk about.
Definitely.
Yeah. Yep.
Take a couple minutes.
Yep.
Because there's no library or something. That engineering investment, yeah, 100. I took the over with you. I took the over. In a couple weeks, it would have been better.
This tastes like Phantom, but it's just
I mean, this was
That's
just
hard.
pops.
that's scary.
Oh, this is what happens when I have to answer. Not physically intensive sport for a while. That's specific. Like that.
Professional.
I was really
Professional Beyblader.
watch the anime. That was actually me.
Oh, yeah, they did that kind of like capture.
Yeah,
Mhm.
I used to think like I could speak to the Beyblade.
Just the way when you roll a bowling ball, you
Exactly. Well, no.
Oh, man. Yeah, Beyblade it just on my shoulder anymore. I ripped it right out of my sock.
We'll start in 1 minute.
Beyblade elbow, tennis elbow, Beyblade shoulder. It's the same thing.
Same thing.
Same thing.
It's a really intensive sport.
I'm gonna go get my Tommy John surgery for my Beyblade arm.
Are we?
It's alright.
Yep. We sure?
Yes.
Where?
It's recording.
Red dot here.
Oh, it's kind of blinking.
I'm gonna say I don't have my glasses on. That's my excuse. All right. Showtime? Yep. All right. So,
Can you select the right number? Is the right mic selected?
oh, here, top one.
We're good?
Yep.
Hey, everyone, what's going on? Thank you guys for coming out to our first meeting of spring quarter. It's great to see you guys here. I hope you guys had a fantastic spring break and are excited for the quarter that we have planned ahead. I see a lot of new faces here, a lot of familiar faces. So it's great to see you all again, and it's great to see some new people this time around. And at least for this beginning part of the meeting, we're just going to go through some basic information. We've got a couple updates on what we're going to be doing this quarter, a couple of Sky's No Limit updates, and something on Spring Give as well. So thank you guys for coming out. Without further ado, let's get into our calendar for the spring quarter. So this quarter is going to be really different from the past two. If you're with us in the fall, we had system, if you guys remember, where we spent 1 week on just going over the general topic and another week on a notebook, and it would be a proper workshop. Last quarter, we kind of did a hybrid of that. Each week was a new topic, and with each topic came a workshop, like a collab notebook or some kind of code to work on, right? But this quarter, we're going to be doing something different, right? We're going to be having a combination of all three, but split into different meetings. We're going to have workshops, discussions, and talks, right? Workshops where we're going to be going over, similar to last quarter and in the fall, we're going to be going over a concept in machine learning and in artificial intelligence. But along with that, we're going to be having our code as well, right? And giving you guys a hands-on experience with how the actual code works, how what you're learning here applies to how you can actually see it being applied, get you guys hands-on with the code, right? Secondly, we have our discussions and talks. Now these, if you guys were here for our last meeting of winter quarter, it's going to be very similar to that, where we're going to start branching beyond the technical aspects, but we're going to start going into some of where it can be some of its applications. We're going to start getting into more ethics. Like, for example, if we look at our calendar, we're going to have a lot of, obviously, workshops. So that's going to be today with Introduction to Generative Models. Next week, we talk about decision trees. On the 18th, we talk about diffusion. And on the 25th, to round out our workshops for the quarter, we're going to get into a basic introduction into computer vision, right? the way that the calendar is organized is we've started off with the workshops, then we get into some of our discussions and talks, and then we're gonna end our last 3 weeks here into getting into more with the Sky's No Limit competition and really pushing you guys in that direction with helping you guys out, obviously with Nautilus. And we have a fully dedicated meeting to the Sky's No Limit competition before the actual submissions. So if you guys need any last minute help, any questions in particular, we're all up here. We're missing another one of our instructors up here, but he'll be here for that meeting. And any help that you guys need, we'll be here to answer that so that you guys have your projects up and ready to go for the next week, right? So let me go through the calendar. We're going to be posting this to the slides to the Discord later, and we're going to be posting our calendar to our website as well. So if you guys need a double check and a refresher. So today we're going to be going over generative models. On the 11th next week, we're going to be going over decision trees. On the 18th, we go over diffusion. On the 25th, we have an introduction to computer vision. On May 2nd, we have our first talk on autonomous vehicles and the harmony between perception and machine learning technology. On the 9th, we talk about AI safety. On the 16th of May, we talk about responsible data science as the last kind of discussion talk of the quarter, and we head into our last 3. So on the 23rd, we have a full workshop dedicated to Nautilus and how to use it, how can you use it how can you fully take advantage of it, and how you can use it for your projects for the Sky is No Limit. On the 30th, we have a full workshop. So like I said, if you have any questions for us, anything you want to go over, you want to try something, but you're not sure, that meeting is going to be fully dedicated to the Sky is No Limit. And then lastly, on June 6th, we are going to have, just like the fall and like the winter, we have the Sky is No Limit presentations where groups or individuals will be able to come up, present, and then at the end, we'll pick our top 4 winners, and then we'll be handing out prizes as that goes. So that's our schedule for the spring quarter. If you guys can't make any one of these, don't worry, all these are being recorded. We're going to be posting them to our drive, and you guys will be able to see them afterwards if you guys are interested in that as well. Also, if you feel like, you can mark on your calendars which one is the one that you're looking forward to the most. So maybe you really want something, you've been really looking forward to responsible data science, you can always pop into that meeting. These are not, like last quarter, these are not building on each other. You can pick and choose which one. Each time is a new learning opportunity. So anytime you guys have any questions, you can also feel free to ask us, right? We're going to be continuing with our speaker event series from fall and the spring. We've usually held them on Thursdays. We're going to keep it with that as well. So these are the dates for our speaker events: April 27th, May 4th, May 11th, and May 18th. All these events will be hosted on Zoom at the same time from 6 to 7 p.m. So it'd be great if you guys can make it. It's a great opportunity to learn from professors, industry experts, and researchers on how they're using AI just outside of what we're learning here, outside of what you guys are learning in the classroom. Where is it being used in the field? And how can you guys take some of what they're saying and apply it to whatever you guys want to? It's a great learning opportunity. It's a great opportunity to network with your peers as well. It's a great time for if you missed some of our speaker events from last quarter, but you're interested. We've posted all of them to our YouTube page. So like and subscribe if you guys can. So if you guys can't make it to speaker events, all of these are going to be recorded and we're going to be posting them to YouTube. So you guys can have the opportunity to look at it afterwards as well. So don't worry if you can't make it to these meetings or to our speaker events. You guys will be able to have access to them after, either through our drive for our general meetings or through YouTube for our speaker events. So next up, Sky's No Limit. We have a pretty big update that we are really excited to share with you guys. We wanted to say it last quarter, but it wasn't fully ready yet. But this quarter you guys are not going to be, it's not just going to be you guys competing amongst yourselves. We wanted to expand the scope of and the reach of this competition. So UC Berkeley, UCLA, UC Irvine, and UC San Diego's artificial intelligence clubs will all be participating in the Sky is No Limit competition as well. So within your groups or your projects, you guys, we're going to be having students and members from UC Berkeley's ML at AI Club, UCLA's ACM at AI, use AI at Irvine, and ASC at, oh, there's one more. Oh, hold on. And UC Davis. All and the ACE Club at UC Davis and UC San Diego have all committed to participating in the Sky is No Limit competition for the spring 2023 quarter. So it's really exciting. We're really excited to have them on with us, and we're excited for you guys to compete with them as well. So we're going to be going over logistics of all of that pretty like the next couple slides, but we're really excited to announce that this quarter is the Sky's No Limit is a UC wide competition. So it's a potential for you guys to put yourselves out there, not only with us and with our sponsors, but with the other UCs as well. And it's more of a challenge now, more people, more projects, more excitement, and potentially more money as well. So we're really excited for this, and we can't wait to see what your projects are going to look like in June, and we can't wait to see what the projects from the other UCs are going to look like as well. So let's get into the theme for the Sky is No Limit 2023 spring.
Alrighty, hi guys. This quarter's theme is going to be different from last time. We did brain teasers. It was in line with what we were covering. We did a lot of neural network stuff for those of you who were here. This time is going to be different. It's going to be a lot more similar to what we did in the fall. We're going to be doing something kind of water related, not exactly, but we're going to go with the flow. So take this to mean exactly what you will. You could take it at face value, interpret it very, very loosely is my always is my main suggestion. That's part of the fun. And if you feel like it's a bit too outlandish, just run it by me and I'll probably approve it. Anyway, that's the theme. Now into a bit of logistics. So as we already just said, the competition is UC-wide. So we're going to be competing against not just people in the club, we're going to be competing against other people in the UC system. What this means basically is it's going to be a lot more difficult to win, but in theory, there's also going to be a lot more prizes. So in the past, I know a lot of people have gotten away with maybe starting a bit late, maybe feeling like they could have spent a bit more time. This is the time to spend more time on this stuff. You're going to be competing against people from 5 other campuses who are also incredibly driven. And honestly, shoot for the moon. Even if you don't have an incredibly amazing project at the end of it, it's worth submitting. It's always worth submitting. But yeah, just keep that in mind. I highly suggest everyone starts as early as possible. You have a full quarter. Take advantage of it. We've upped the cap of the number of people in the group. It used to be up to 3. We're increasing that cap to now be up to 4 people in each group. And then we're also going to, with an asterisk, say 5 if you run it by us for specific reasons. Yeah, that's very simple. Final submissions, as always, are on the Sunday before presentations, so June 4th, and then the presentations are on June 6th. And then for those of you who want to sign up right now, this isn't really a sign up or anything. This is just really for you to express interest so we can communicate more directly with you guys rather than making general announcements. If you want to scan this QR code or just go to tinyurl.com/sky-spring23, that'll give us your email name, and we'll be able to send some more direct communications to people who are interested, just so we can avoid a lot of the splatter. Yeah.
Like everyone in the group, they all have to like kind of contribute technically, or is there like now with this kind of being together, is there like more room like people can like divvy up the work and like maybe have a different role in the project management role or like something like that?
I'd say yes. This is the same as before. Not everyone needs to code. You just need to be able to do whatever. The prize isn't going to be the same for every person. Like if last quarter, our top prize was $225. If your group is 4 people big, not each person is going to be getting $225. It's going to be split up, understandably. The restrictions basically are only one group per you can only be in one group because you can't just spread out and do 17 different projects and submit all of them to maximize your chances of winning. It's no fun. But if you're not going to necessarily contribute technically and do something more managerial or presentation aesthetically, it doesn't really matter. Then I'd say go for it. Getting more people involved, I think, is very important. People with different perspectives who aren't necessarily technical can contribute in important ways. Any other specific logistic questions for groups? Yeah.
This is for groups, is it affiliated with specifically the UCs themselves or specifically the clubs at those campuses?
The clubs at those campuses.
Okay,
Yeah.
so specifically the clubs, all right.
The main, or at least the clubs who I've reached out to have reached out to me regarding this. So we're working with the most active clubs, I would say, the most active artificial intelligence clubs at those campuses.
Okay, thank you.
And I will also say that have we talked about allowing people to work with groups between campuses? Right. So if you want, this also is an opportunity to work with people between campuses. So if you want to work with someone who's at Berkeley or Irvine or Davis or whatever, they just need to submit and be a part of the presentation. And that's basically it. So long as the school's already participating, as we covered here, we might add more as the competition grows. So long as their campus is participating, feel free to add them to your group, have them contribute. They'll just be splitting the prize.
And do they have to be in the club at their schools to participate?
I mean, if it's anything like our club, you know, the conditions for being in it is just joining the Discord more or less. So again, as long as they're active, I'd say at least partially in the club, then
Have like, you know, very strict, like.
Yeah.
Yeah, I can't imagine Berkeley AI classes that easily.
really?
Yeah.
Oh. You have to go through interviews for wow. I doubt it. I have faith in us, especially since we're running it. No favoritism though. So just try your best. The main thing that you're going to get out of this is learning how to use the frameworks, learning how to piece together some sort of project. And most importantly, data science. That's what I've been pushing this entire time. We cover a lot of models, but learning how to manipulate and manage data effectively is really important and not something that we can teach to you directly. So a self-managed project is very good for that. Yeah, no, I think you guys will be fine, probably. Yeah, no, if you want members of the group specifically for Berkeley, we might need to look up specific exceptions to this, but I don't see why that might be a specifically limiting factor. Anything else? Cool beans. All right, who's doing Spring Give? Dylan.
I also kind of to talk about the money side of things now. Right now we have Spring Give going on. It was started on this Sunday and is running until next Tuesday. It's a $5 minimum donation. It's kind of annoying that they set it at that, but there's like a couple challenges that are based on like how many total donors you get. So I guess it kind of makes sense, but that's the minimum. We're just collectively fundraising for Sky's No Limit this quarter, and then kind of other events more generally. I think we have some aspirations of having some sort of club kind of end of year thing here as well, like a little bit more of like a potluck or like kind of like social get together. So fundraising for that stuff. And I'd say this is primarily focused on, you know, industry and corporations. These donations are tax deductible. So we're really kind of, we think this is a really good opportunity. I think a lot of people in Silicon Valley like to talk about how philanthropic they are, but they like to see that they can get their money back on their taxes first, usually, in my opinion. So I think that will possibly be fruitful. But the donations from any of you guys in this club is very appreciated, especially the people who have you know, won Sky's No Limit before. You can kind of think about, you know, paying this back into the pool almost. But yeah, so anyways, this has the potential, I think, to, you know, really help us make this event this quarter really great, but also help, you know, us meet our fundraising goals for next year. We've really tried to like have you guys be able to participate in this club with no strings attached, ourselves included. We don't want anyone to have to pay in money or like have to contribute dues. I know some people who pay like $80 to participate in a club that doesn't do anything. So, you know, if you want to donate, you can donate. We're going to continue to kind of like, you know, I think, have the same sort of model, but, if you could spread the word, or, you think that, what we're providing here is valuable, any support is greatly appreciated. Yeah, that's it.
Yeah, and if you know people, let them know. If you're going to participate in the competition, this will probably increase the prize that we can give away. It'll also help us run more events. Just shill it to your parents, shill it to your aunts and uncles, shill it to your older siblings who are currently employed by Google. Really, anyone with money.
Yeah.
We like it. And speaking candidly to all of you, the main reason that we haven't been able to run more events, social events, what have you, is because we don't have much of an income. Most of the time that we spend working on club stuff is instructional. We would love to be able to host more events. Truly, it would be really fun. We just don't have money. So like, just
Hard to get money.
Oh yeah, that
This is
too.
a really good opportunity to get a lot.
Yeah, so if this goes well, in just terms of total number of individual donors, there's additional awards from the school that we can get. In terms of the most in a specific window, we can get a whole bunch of stuff. Anyway, spread the word. We'll be making announcements as the fundraising competition goes along. And in theory, if this goes well, we'll have our operating budget funded for a while, and we won't need to beg for money at any point. But yeah, that's more or less the logistics. So now we're going to be going on to, I think at least, now we're going to be going on to GANs and generative models at large. So off to Cohen.
All right. I have to reshare the screen. No, remember the whole thing. All right. Give me a second, guys. Oh, that's the wrong screen. All right, hopefully that should work. All right, everyone. So we're going to go on to our next part of the meeting, which is introduction to generative models, at which point we'll go into a bit of a deeper dive into a specific generative model, which are known as GANs, also known as generative adversarial networks. You have to select just click on the slides. Yeah. Okay. All right. So if you've been with us at previous meetings, a lot of what we've done before are what are called classification models. The way classification models work is they get a bunch of data, and their main job is to either predict or classify the class of a specific data type of data. So, for instance, if you're given the flower that you're given, let's say the color, the height of the stem, the number of petals, all of that, that'd be considered a classification model. And so the goal, given all the information, figure out the class of that object. And so we've learned about a bunch of different algorithms for that. So we can see here, we talked about clustering before, regression, neural networks, a bunch of other things that we covered in previous quarters. And we'll continue covering these again this quarter and probably for many years to come as well. Another type of model are called generative models, which are kind of like the opposite of classification. So instead of trying to predict something or the outcome or the class of something based off of a bunch of data, we're using the class of an object to be able to generate content or the data for it. So for instance, in classification, you might take an image and identify something in that, whereas generative models, they might take the type of image and then actually generate that image. And so there's many use cases for that. And one of the biggest ones that we've seen a lot of is image generation, and also technically chatbots like ChatGPT is considered a generative model as well, just because, again, it generates a response to whatever you give it. So some models that are generative models are autoencoders, generative adversarial networks, which we'll go deeply into today, and diffusion models, which we'll talk about in 2 weeks' time. We'll go a bit more in depth. But for now, we'll go into a brief description of what each of those are. Oops, wrong way. So autoencoders. So autoencoders were kind of thought to be as the first generative model, kind of started off and theorized in the early 1990s. And the way these essentially worked is they use these neural networks that we talked about a bit last quarter, and they take an image to begin with, and they're able to add some version of compression to that original image to get what's called the code. We'll talk about this a bit later, call it seeds or latent space, but just know that we take original image, we compress it into something smaller using this neural network and a bunch of connections in between each layer. And we then use that code and we decode it again using that neural network to generate our new image. As you see here, we start off with this original image. We add some compression to it, which gets us this really not very helpful code, but we're able to then denoise that into a output image. So that generates new content. And as we can see here, it's not the best model here. You can't generate brand new content with it. And even the images that it gets outputted aren't the best, right? And so we took a step out from here into what's called the GANs, or wrong direction again, the generative adversarial networks. So GANs were introduced in 2014, were this huge introduction by Ian Goodfellow. And the way that generative adversarial networks work, in brief, is that it has two components, which are each neural networks themselves: the discriminator and the generator, with the generator being the one that generates an image, and the discriminator being a classifier that tries to identify whether the given image is a real image from the training data set or a generated image from the generator. We'll go more into this in future slides. This is just the brief introduction. And nowadays, we use, this is the wrong slide again. Nowadays, we use what's called diffusion models. These were inspired by physics in the non-equilibrium thermodynamics department. So if any of you guys know anything about that, wonderful. I couldn't figure out too much about it. But diffusion models work very similarly to those autoencoders that we talked about earlier, where they use a Gaussian noise distribution to kind of add noise or diffuse that input. Remember we talked about how the autoencoder compressed it and then uncompressed it using encoder and decoder? This does a similar thing where it takes that input, diffuses it, and then goes through the reverse diffusion process to come out with a new image. So these are the state-of-the-art model for this kind of like image generation. We'll go into examples of this in another week. But the main idea is that it uses this a bunch of neural networks to take an image, diffuse it, and then learns a way of reverse diffusing it into that image that we get as an output. All right. So many of you guys have probably actually heard of some of these examples. We have here Stable Diffusion and DALL-E 2. Raise your hand if you've heard of at least one of these before. All right, a lot of you. All right, that sounds good. So these are both text-to-image deep learning diffusion models, meaning that you give it some amount of text and it gets you an output. So for instance, if we look at the image on the right, this is an image created by DALL-E. And so we gave it as an input an armchair in the shape of an avocado, and it created this image, which has never been before seen, of an armchair in the shape of an avocado. Pretty impressive. So both of these are these much larger models that will take a lot of computational power to train, and were built by Stability AI for stable diffusion. And DALL-E 2 is built by OpenAI, which if you've heard of ChatGPT, those are the same people, the OpenAI group. So kind of a brief description of how DALL-E works is it uses a combination of the CLIP model, which is a method for taking in that readable text, which uses some natural language processing to convert that into some form of seed for our diffusion model to then generate an image through. And so a combination of CLIP and diffusion models is how it goes from that text into a actual image. If you want to talk about that more later, I'm happy to figure that kind of stuff out after the meeting. So what we're talking about mainly today is, again, that generative adversarial network. So what does this mean? Well, let's first look at the concept of an adversarial network. Adversarial in this case means two things, or something that goes against something else. So for instance, think of like an edge case for some algorithm. Something like that is an adversarial example. And so the way that it works is, again, it generates these fake images based on training data using these two neural networks, or two different agents. Again, as I mentioned before, that we have that generator and the discriminator. I'll go into a bit of an example in a bit. And they go, two of them, the generator and discriminator, go against each other in what's called a zero-sum game, where they both try to one-up the other. So a zero-sum game, for instance, tug of war will be a zero-sum game, because in one case, when one person, pulls the rope toward their side, the rope gets moved away from the other person. So was one person gains, the other person loses, or the other agent loses. So hockey or basketball would not be considered zero-sum games, as no matter what, when one person gets a point, the other team doesn't lose a point. It just keeps going higher and higher. So what does this necessarily look like? Well, this is a little diagram I built here for what the architecture of a generative adversarial network looks like, where we have, again, our discriminator and our generator here. And so we can start off by kind of going through what might actually happen. So let's say we are trying to train our GAN to make fake images of stop signs. So as we see here, we have our real image database. This is the data set of real stop signs that we want to give it. And so this real image gets sent to the discriminator. And the discriminator's goal is to be able to identify whether the image given to it, is it from that real image data set, or is it an image generated from our image generator here. And so right now, it doesn't really know anything. It hasn't learned anything yet. It's the very beginning. So it makes a random prediction. Let's say it predicts correct. It says, hey, I think this is a real image of a stop sign. This will tell our discriminator, hey, look, you did a good job. You guessed correctly. And it will try to learn from that. So it says, maybe it tries to find a pattern within that stop sign. We'll say, hey, whatever you did, do more of that. And it learns a little bit from there. So our discriminator is slowly getting better. So what if then we generate a new image? So again, our generator hasn't learned anything yet. It creates this image from a random seed. And so right now, as we can see, it's just a blob of colors. There is no stop sign here, but it just creates something from a random seed, as we see with random number generators. And so this fake image gets sent to our discriminator. Discriminator, again, has to be able to identify, is the image given to it a fake image or a real image? And let's say it gets it right in this case. It says, hey, I think this is a fake image, which is correct. And so from that, our generator will learn, hey, maybe don't do that in the future. It'll learn from its mistakes and hopefully get better as it generates more and more images and gets feedback from our discriminator. Discriminator will also learn, says, hey, you got it right. Keep doing that. You're on the right track. Learn whatever was in that as to not do this. And so this will continuously happen where the discriminator will get both a real image and a fake image from the generator, which will cause both of them to learn and grow better. And so in some cases, right, as we see here, our generator created a much better fake image of a stop sign. So as our generator gets better, it's going to be more likely to fool our discriminator, right? So now our discriminator, when given this fake image, might mispredict it as a real image. As we can tell, this is a fake image. And so it will say, hey, I did a poor job. And so it will learn maybe to notice some details, maybe that now it notices that this doesn't say the word stop, so it probably isn't a real image. And the generator will learn, hey, keep doing that, you're getting better. And so these two will keep fighting to get better than one another, where the generator will keep trying to make those better images. For instance, it might then generate this. And our discriminator needs to keep getting better to catch up with what the generator is keep creating. And so as you see here, we might get an example of a stop sign that looks like this, which is a lot better than we started with. But if you look carefully, you can see there are a couple flaws. And we're able to get that continuous feedback cycle where both the discriminator and the generator learn. And again, that zero-sum game. So this is an example of a GAN that was trained on a bunch of stop signs of different colors. It was a kind of an interesting experiment because the input that we gave for this GAN were actually a bunch of fake stop signs that are created by Dolly. So we're creating a generator for fake stop signs based off different colored fake stop signs. So this is kind of the process it went through of learning what to create. So around one of the first couple of epochs, as we can see, it's just, again, this random noise, right? You see just a bunch of colors. The generator clearly didn't know what it was doing. After a couple more epochs, it started to learn the general shape of what a stop sign might look like. And again, we see all these colors because I did give it a bunch of different colored stop signs. So if you look carefully, I don't know if you guys can really see, but they're okay pictures. You can see the general shape of a stop sign, but most of the time there is no text. If there's anything even there, it's just gibberish. And after another maybe 10 epochs, it slowly starts to get better. Maybe the shape becomes more well-defined. The background you can start to see is a little bit more meaningful. And all of a sudden, after a full day of training, I got a really interesting result, which is, for some reason, all the stop signs it generated we're slowly starting to become more red. It's just one of those interesting cases of how you never really know what you're going to get out of these models. They're not perfect. And so even though we trained it on a bunch of random colored stop signs, it still figured out that it should make a red stop sign. That could be a whole research paper, but it's just something interesting to learn. And I trained this using the StyleGAN3 architecture. So let's go play with this on our own. So as you see here, I'd like everyone to open up the Colab notebook so we can actually play with some code. And I'll leave this up for later. So everyone can go to the link there, and that will be a Colab notebook that everyone should copy before you make any changes. So if everyone can make a copy of it, then you can play around with it as I go along.
It's also really important this time because this will take probably 30 minutes at least to train.
Yeah, this will take a long time to train if we use all 100 epochs. If you guys run it yourselves, I suggest using closer to 20, in which case it'll take like 10 minutes, hopefully. But yeah, well, there's already an example shown there, which I'll show on the screen. Yeah.
Is it parallelized?
This one should be parallelized. I don't remember exactly, but it is using the GPUs. So yes.
I thought it'd be using all the, I thought it's like I meant more like it's multi-threaded or something.
We are using the PyTorch framework, which we'll see in that automatically parallelizes everything. Yes. Exactly. Yeah. Just that'll make it so you can edit it because right now I'm pretty sure it should be shared as view only for everyone. All right. Does anyone else need the link before I go into the actual code? Cool. Let's get into it. All right. I gotta reshare the screen. Yeah. All right, does everyone see something that looks like this, right? Yes, everyone's good. Perfect. All right, so again, we have here just a general model of as to what our GAN will look like. We have our data set. In this case, we're using the MNIST data set, which is a bunch of handwritten numbers. So digits from 0 to 9. And we're going to be able to try, our goal is to try to replicate this and kind of design our own digits using this model. All right, let's get into it. So these first couple of cells are kind of just the basic imports and setting up our data set and our data loader. So part of this, as you know here, we'll be using the PyTorch and NumPy packages. Previously, we've used TensorFlow and a little bit of mixture of PyTorch. So you'll get used to the syntax in a bit. So the first part that we want to do is we're setting up the data loader. This allows us to be able to load all of our data in smaller chunks to make it a little bit easier and faster for us to train it later on. So this says when we want to get new data to train, it gives it to us slowly rather than all at once. So right now, we don't really necessarily have to play around with these values. These values just are good for the hardware that we're using currently. Now we have our data set. So this is kind of just to view what our data looks like. So as we hear, this is a 5, I think. Yes. Probably wouldn't be a good classifier for this. Maybe a computer is better than me. But this looks like a 5, and this is just an example of what a piece of data from this MNIST data set looks like. So if you want, you could play around, change which number you actually want to look at through here. Right now, this is just the 0th image. So play around, maybe see what that looks like. Oh, actually, first off, I'll ask, so everyone used a Colab notebook before? So everyone understands? All right, perfect. So if you ever want to run a cell, make sure you run all the previous cells beforehand, just making sure. It's not letting you run the first cell. What does it say? Ooh, I have never had that issue before. Usually it should have that already installed in the kernel. Is anyone else having that issue?
I mean, you can also just try and do pip install. Yeah, so if you're having that issue for some reason, do !pip install 40, I think is the
something like that. Yeah, Rahul will help you. Hopefully we can get that settled. All right, so The next step is to actually start defining our model. So as we talked about earlier, we need to have two components in our model, our discriminator and our generator. And so these are going to be our neural networks that will both classify and generate these images. So let's start off with our discriminator. Who here, or raise your hand if this looks some things that you've seen before. So if this looks familiar, raise your hand. Just trying to see what we should go over. All right, I can go into this a bit more in depth. So if you don't remember, actually, let's ask. Raise your hand if you've seen what a neural network has looked like, or know what one looks like, or knows a little bit about them. Okay, so most people know what a neural network looks like. So I'll go over a quick brief description of that. A neural network, think of it as a bunch of layers of dots, right? Where each layer has a certain amount of dots that store information. And each layer is connected to the next layer through a bunch of interconnections. So every single node or dot in the previous layer is connected to the next one. And how they're connected kind of determines how it gets predicted or generated as an output. So all these connections, and so the number of nodes per layer or helps you build these neural networks. And so once we're able to train it, all of that will then, all the different nodes will help identify whatever the common goal is. So each of these lines right here, so we're seeing like NN linear, this is what's defining a layer. So our first layer, as we see here, has a input size of input size. In this case, our input size for a discriminator is going to be whatever the size of our images are. In our case, our images are 28 by 28 pixels. So our input size would need to be 28 times 28, whatever that is. Sure, whatever that is. And the output of a layer is whatever we want. In this case, we're doing the hidden dimension. So that's just a parameter to our class times 4. And that's the size of the output of that layer. Therefore, the next layer needs to take in an input of that same size, give it another output, and it needs to eventually come out to whatever output size that we want. So once all these are connected, they need to be sent out to whatever size we need. In our case, with our discriminator, how many outputs should we have? Can someone take a guess at this? That's your answer, 2? Yes, so the answer would be 2. We'd want 2 outputs. Either it's a true, it's a real image, or if it's a fake image. In this case, because all of our stuff is binary, we just need an output size of 1. It's either 0, 1, or in between if we're not 100% sure. Is everyone following that so far? Can I get a thumbs up, thumbs middle, thumbs down? Pretty good. All right, well, we'll keep going. So as you see here, that's where we define each of those layers. If you have questions about neural networks and how they work, come talk to us afterwards, and we'd be more than happy to talk more about it. So this is where we actually build that neural network. So we add a bit more complexity to it. So as you see here, we add activation functions. These activation functions help kind of remove the linearity from our neural networks. As we see here, we use the leaky ReLU activation function, which is very similar to the regular ReLU function. So essentially what the ReLU function does is it says, if the value it's given is less than 0, just set the output to be 0. If it's greater than 0, just the output is equal to the input. So we quickly draw what the ReLU looks like. Sure. And similar to that, a leaky ReLU is very similar in the same way where if it's greater than 0, it is whatever the input is. And if it's less than 0, it is some percentile of whatever that value is. So for instance, if you give a leaky ReLU the value of 10, the result is 10. If you give a leaky ReLU -2, you might get out -0.2. Unlike a regular ReLU, where if you give it -2, it just gives you 0.
Yeah, so mathematically, real quick. Leaky ReLU is over here on the right, multiplied by something from alpha fractional. It's negative below the x-axis. That means it's inhibitory. It reduces the output of the and then just typical ReLU is divided by x-axis past 0.
They're used usually in SVX, correct?
ReLU is used everywhere, but leaky ReLU, Maybe, yeah, I have no idea.
I remember there's like a function that's like, that the ReLU tried to improve on, which is like a smooth version of the ReLU, where it just curves upwards.
Oh, yeah, remember that function, I think you're right, though. I'd have to check. Any other questions about this? This is used basically everywhere.
Perfect. So we'll keep going on. So if you remember from a previous meeting, we talked about the concept of a dropout layer. If you don't fully understand what a dropout layer is, don't worry about it. It just helps build the neural networks to be more efficient and have less issues later on. Just debugging things, right? So that is our discriminator. The main idea is that it takes in an image of size 28 by 28 and gives out a classification, either a 0 or 1 or 0 or something in between, which identifies the confidence level. So if you know a bit more about neural networks, you can kind of piece apart this and see how it better works out. The next model that we'll be building is our generator. So this works in the opposite way of our discriminator, where instead it will take in a random seed. So we'll talk about a bit about this later. This is also going to be known as a latent space, just a random seed to be generating our image from. So this takes whatever size that is, throws it through our neural network again, which has a bunch of different layers of different sizes. And our output is going to be a 28 by 28 image. And so this creates our fake image. And you can see here, we use a very similar network as our discriminator. There's a couple differences, which I think I mentioned in the text above here. So if you want to read that on your own time, go ahead. And this will get out our results. So one thing to mention, I like to mention, is our output is whatever the neural network is outputted, but pushed into a tanh function. This just helps normalize the values between -1 and 1. So if later on you might see some normalizing happening, this is why, because we threw it through a tanh function. Yes?
Why the tanh function in particular? Because there are a lot of functions that are scaled between that.
Yeah, it has to do with the curve. Like sometimes this will like push more of the results to be either closer to that -1 value or that 1 value. So for instance, you could just use a linear line but cut off at -1 and 1. But this case, just because of that curve, it makes it so that the values are more concentrated closer to 1 or -1.
It's roughly the same reason people use sigmoid. Sigmoid is just I think it's the derivative of the normal distribution. Doesn't really matter. The point is basically it amplifies differences close to 0, which means that you're going to see a lot more differences from something that's like 0.2 and like 0.2 above 0 and -0.2 below 0, where otherwise differences are really good for telling differences that aren't super far apart. And then also it just allows you to have more. Yeah.
Why not use something like the error function? Because it's very similar to the hyperbolic tangent. Error. It's the integral of e to the -x squared.
There's a lot of different things you can use. It really depends, and you can test it. Maybe it works better, maybe it doesn't. For this case, we found this one to work pretty well. That's actually something that you guys can play around with, swapping around these values a little bit later on.
Yeah, if you look at the API, there should be a way to custom.
Yeah. So for everyone that this is probably going over the heads of, don't worry, as long as you understand the concept of there being two neural networks that kind of compete against each other, that's the main idea. If you're here at previous meetings, these kind of key terms will kind of, you'll understand it a bit more. If you have questions again, don't worry, you can talk to us about this later on. All right, so we have our two networks that go against each other, our generator and our discriminator, and we can go into actually setting these hyperparameters. So as you see here, we have our input size, which 784, which is again 28 by 28. We have our output size of our discriminator, which we talked about earlier, which was just a size of 1, because all we're doing is it's either 0 or 1 or something in between. We have our hidden layer size. This is something, if you want, you could play around with. In this case, we thought that 32 seemed to be a pretty good value in terms of getting accurate results. Changing this just changes the size of that neural network, and you can play around that. Maybe there's a better value, up to you guys to figure out. Now we have the Z size. This again has to do with that random seed. So if you want, you could play around throwing different values into here. This just has to do with how are we actually picking that random variable for the seed of our generator. And again, we have our generator output size, which is the size of our image, again, 28 by 28, and then the hidden layer size of our generator again. You can play around with those a bit later. It's just using these just to see what it looks like for now. All right, and then we can see just building it together, we get our discriminator and a generator with these different features. So you can go look at that a bit later. So now we have to talk about loss. So I know you mentioned loss a bit, but we'll go a bit further into it. So the concept of loss is an important piece of identifying how well is our model performing. So to be able to identify, the performance of these models, we have to calculate the different losses of it. So as we see here, we have our two functions of loss. We have our real loss and our fake loss. So that means given a prediction, we have to be able to identify how well it did. So as you see here, we are using the binary cross entropy with logits loss. You don't really need to know exactly what it is, but that just helps identify how close the discriminator predicted. So for instance, if the discriminator was like predicted it was a 0.7, meaning it was pretty close to being a 1 or a fake image, it would then say, oh, it's using the binary cross entropy loss function, it identifies the loss to be, let's say, like 0.2. So it's pretty close, but not exactly, right? Because if it's a if it's a fake image, then we'd want it to give a 1 out instead of a 0. These are just used for identifying the loss. And so real loss and fake loss, pretty much exactly the same, except for the fact that with real loss, the goal that we're comparing it to is a 1. And with fake loss, the goal is we're trying to compare it to a 0. If we see here the concept of smoothing, so if you want, you can turn this flag on or off. If it's on, smoothing just compares it to 0.9 instead of 1. Some cases, this might result in a better GAN. Some cases, maybe not. Again, these are one of those things where you can tweak it, see how it works, and play around with these values. That makes sense, just the general overview of a loss function. Everyone's good? All right, well, we'll keep going. Optimizers, I'm not going to cover optimizers too much. This basically determines how it calculates in which direction it should change the different weights and pieces of the neural network for training. We use the Atom optimizer with a learning rate of 0.002. You can play with the learning rate. I'd suggest staying anywhere between 0.01 and 0.001. Tweaking around there, maybe you get a better result than this. These are just the default values we're using. Atom is a really good optimizer. If you don't know what an optimizer is, probably don't change that. So the actual training part of it. So for training it, we have to do 2 versions of training. We have to 1, train the discriminator, and 2, train the generator. So we're going to do this in 2 different parts. As you see here, this is where I'd like everyone to change the number of epochs. Instead of 100 epochs, if you can all just change it to something smaller like 20. So if you leave it as is, it will take, if you could see in this corner, 40 minutes to train with only 100 epochs. So if you want to be a bit faster, you can lower that down to a much smaller number. Again, an epoch is just the number of times it does the training loop. And so these print to every is set to 400. So every 400 things it looks through, it will print the results, which is basically telling us the baseline of how it's doing. And this can help us identify if there's any major issues later on. This part right here, the sample size, again, that's for picking out how many images we want to actually get and train at a time. That has to do with data loader. You don't have to worry about that too much. And then our fixed Z, that again has to do with that latent space, the random number seed. If you want to mess with this, go ahead, but I suggest keeping it like this for now. All right, so now we want to set both our discriminator and our generator to be in the training mode. This will help set the weights and values of our neural networks so that can correctly predict or generate our models. So we look into our actual training method now. We want to loop through however many epochs we say to loop through. And now we want to go through different batches. Each batch is a set number of samples from our data set as we kind of defined earlier in our train loader section. So we can start off by kind of rescaling the images. Remember how we talked about we using tan H and having a range of -1 to 1. So we rescale it a bit, and we want to start off by training the discriminator. So the first step is resetting our optimizer to be the gradient to be 0. This is just the standard step. And then we want to get our predictions. So given a bunch of real images through our discriminator, it will give us all of its predictions for those real images. That's what we do on line 40. Given those real images or those real predictions, we want to throw it through our loss function as we defined earlier. And so by predicting whether they are real or fake images, we can then get the loss of our discriminator. And so we do the same thing here. So we have these two steps, which finds the predictions and then calculates the loss from it. Additionally, we do the same thing here with the generated images. So we give our generator that Z, which is again, that random seed, for it to generate a bunch more fake images, which then could then be given to the discriminator. So same steps as here, but we give it fake images and get the fake loss. We combine the two to get our overall loss, and we're able to tell our discriminator network to learn from that, which is our backward and step method here. So I would suggest not touching this. This is just the general training process if you haven't seen neural network training in PyTorch before. If you look now, we can start the training for the generator. This is very similar to what we saw above. So again, we zero out the gradient, we get that random seed, and then we can actually generate those images from that seed, which gives us our fake images. Again, we give those fake images to our discriminator, which give us our predictions, which we can give it to our loss function, which gets us our generator loss. And we train the neural network based off of that loss. Does anyone have any questions about that? No, can I get a thumbs up, middle, down, see how people get it? Yeah, question.
Right before it does the other stuff, it says d.train and g.train.
Oh, yeah.
What's that referring to?
I don't remember exactly, but I'm pretty sure that has to do with just setting those networks to the training state.
Oh, okay, so it's setting a state. That's not actually calling the training. It's not actually training them there.
Yeah, yeah,
Okay.
exactly.
What's a training state usually? Like all zeros or something?
It's just allowing you to actually use this.
Yeah.
So if you, if for example, which was for the last quarter, if you do something with transfer learning, you're gonna want to lock the weights of the pre-trained network. You don't want to redo the values of that. It's gonna not be very. It's gonna be expensive in terms of time, and you're not gonna get better results. So if those layers aren't set to be trainable, then you can just train whatever you add on, get an output. And if you have that, the training flag set for all of them, then you're gonna have a lot more to go through. It just becomes a more expensive process.
I would love to go into this in a bit more detail, but we are going over GANs and not necessarily neural networks. If you have those questions, come to us. We have tons of resources from previous meetings and everything to go help guide you along the way of neural networks, as they are a component of pretty much everything in modern deep learning. So once with everything trained, we can then kind of view everything. If you see right here, this is the pickle file. Pickle files are just basically the state of the neural network that we saved and we can use later on. So as the program goes, we can see the print statement every however many steps. We say, oh, print the current status. So as you see, when I ran it through 100 epochs, it started with a discriminator loss of 1.3, generator loss of 0.7, and it slowly changes over time, where as one gets better, the other one gets worse. And this is, again, plotted in the next cell. So again, this just plots the discriminator loss and the generator loss over time. So notice how as one goes up, the other one goes down. That's where we have that concept of that zero sum game, or I think that's what it's called. And when we actually want to view how well we're doing, we just have a couple helper functions here to view it, and we can select which sample we want to view. In this case, we say, let's view the last sample, which is why we have that -1. If instead we want to view like the 10th sample, you can just put 10 here. But this is how we view samples using the view helper function we have above. And as you see, after 100 epochs, this is the result of our GAN. Again, not the best. It could be a lot better. Imagine if you ran this instead of just 100 epochs, 1,000 epochs, it could probably get a little bit better than this. But slowly, these values are going to become more distinct. So you can tell this is probably a 1. That's a 3, I think. This might be an 8. But the point is, we can slowly start to see different things coming out of it. And so if you want, on your own time, you could make it a number of epochs, 1,000, tweak some values. But this is the general way it works. And we can kind of see the change over time. So this one right here just shows a bunch of them, with this being the 0 epochs, this at 10 epochs, 20 and so on, I think. I'm pretty sure. So we can see that it's slowly getting better, I think. Neat. Yeah. And so does anyone have any questions about the code here? Yes.
I finished running the GAN.
Mhm.
The discriminator losses remained pretty low after it was run 100 times. Maybe is it saving the values somewhere and then reloading those? There's less to do.
What do you mean by the discriminator value is low?
The loss is zero sum game.
The discriminator values are really close to point. Like the generator loss is on the order of 10 to the 1. The discriminator loss is on the order of 10 to the negative 1. That's like,
Oh, wow. Did you change anything?
I changed the learning rate a little.
That's probably, yeah.
That's probably why. What'd you change it to?
0.005.
So that would learn a lot faster. Maybe, again, this is one of those things with AI and these neural networks is you can change things, tweak values, and you get completely different results as we see here. And so that's why we have these default values. These should work. If you want to tweak them, play around with a different number of hidden layers. If you're familiar with how neural networks work, you can change dropout and all the things we talked about before. But yeah, if you want, I think we are done with the meeting. If everyone can fill out we have a feedback form just so that we get a better understanding of what we should cover next time, what things we can improve, what you guys like. That'd be great for us. You could just use the QR code here. If you want to stay here, we'll be here for a bit longer, just to play around with the GAN that you have, given to you guys. Yeah. Thank you all for coming. If you want, you could play around with the code. You could play around with it later. If you have any questions after the meeting, you can always reach us through the Discord if you have any questions. If you want to get a better understanding of other AI concepts, such as neural networks, talk to us as well. We have tons of things we'd like to talk to you guys about. Thank you all. Again, please fill out the feedback form, the QR code, or the tiny URL. It helps us a lot with coming up with better content. And if there's something we missed, you want us to cover more suggestions for how we should better present everything, we'd love to hear it. Thank you. So, yes. Mom just showed. All right, we'll keep this up for a bit and then we can go switch to it in a second.